Hello everyone, welcome back to my channel. In this video, I will show you how to calculate the band gap of silicon crystal using just one single self-consistency calculation. And I will use the standard DFT, which is the PBE functional. So let's get started. So this is the input file of the calculation, and I guess you are more or less familiar with the things inside, so I will not walk you through. One important thing is here that you need to increase the number of bands to 8, so that you not only calculate the valence band but also calculates the conduction bands, so that in the output of the self-consistency calculation you will see the energy of the highest occupied level and also the lowest unoccupied level, and the difference between those two numbers is actually one estimation of the band gap. But you may already know that if you want to estimate the band gap in that way, you need a slightly dense K points. So here we choose 8 by 8 by 8. Actually this turns out to be enough, but we still need to do one convergence test, increasing the K points and see whether the band gap changes, so which we will do in this video. And also we want to do a convergence test on this energy, this cutoff energy, and this E-cut row to see whether we need a higher cutoff energy. But it turns out this is already quite good. Okay, so we can do the calculation here, which is quite standard, and this is quite fast because we only have 2 atoms in one unit cell. Okay, so this is finished, and I can first show you how do you find the band gap, the information of the band gap. So if you scroll down to the bottom, you will see that there is the information of the highest occupied and lowest unoccupied level, and basically the difference between those two numbers is the band gap. Yes. Okay. And then what we want to do is I want to change this E-cut WFC and also the E-cut row and also the K point to see whether the band gap changes. I have done the calculations for different K points. For example, this is 16 by 16 by 16 and 40 and 160, and for example here we do it for 80, 320 Rydberg, and the K points density are 16 by 16 by 16. And then I've already done the calculation, so to save time here, and then I have already put the result here. Yeah, so basically this is the difference between the lowest unoccupied level and the highest occupied level, which is basically the band gap. And you see that it converges quite quickly with respect to the energy cutoff, and also if you increase it from 8 to 16, actually you do not double the K point, but you actually multiply the number of K points by a factor of 8, but still the band gap estimation is very close. So that's why in the hybrid functional calculation we will use a 8 by 8 by 8 grid, because it is so expensive we cannot afford the 16 by 16 by 16 grid. Yeah. So in this case, let's say we just take the value here, this 8 by 8 by 8 and 40 and 160 Rydberg. We just take the band gap here and copy it to here. Yeah. Okay. And then you will see that the difference between this PBE calculation and the experimental value is quite large. Yeah. And the standard DFT underestimates the band gap quite a lot. So in the next video I will show you how to calculate the band gap using HSE hybrid functional, and we will see that it actually gives a much better estimation of the band gap. So thank you for watching. I hope to see you next time.